9 HSC. Question 2. Okay, so again, first question. I to the 9 in a plus ib form. I to the 9 is I squared. We write it in terms of I squared. I squared to the power of 4 plus 1 more I. I squared is negative 1. Raised to an even power is positive 1. So it's simply equal to I, which is 0 plus I. Part B, negative 2 plus 3i all over 2 plus I, again in a plus ib form. So we're going to multiply this time by 2 minus I, the conjugate of the denominator, to realise the denominator. So we get negative 4 I, negative I times that is negative 3i squared, which makes plus 3. 2 times that is plus 6i, and negative I times negative 2 is plus 2i. On the denominator it's a difference of squares, so we get 2 squared, which is 4, and then we get I squared, negative 1 times negative makes plus 1. So if we have a look here, we get negative 4 plus 3 is negative 1, so make it negative 1, denominator is 5, 6i plus 2i is 8i, so plus 8 over 5i in a plus ib form. Just move it on. Okay, part C asks us to plot a few numbers given that we have z here and q, which represents w here. The first one is r, representing the point iz. So for iz, we know it's just multiplication by 90 degrees, so the modulus doesn't change, but we just multiply it 90 degrees, rotate 90 degrees. So this point out here, r, is going to be iz. Next point is s, which represents the conjugate of w. Conjugate of w is just a reflection about the x-axis, so that'd be s, the conjugate of w. Next point is t, representing z plus w. So z plus w is just the completion of the parallelogram, so I'll draw this line in. I'll move it up to here and draw it up there. Complete that parallelogram, and this point up here is going to be t, which is z plus w. Part D, you had to sketch a region in the Argand diagram, a complex plane. First inequality was z minus 1. The modulus of z minus 1 is less than or equal to 2. We know that's a circle with radius to centre 1. And when you draw these, you probably should draw them relatively accurately. At least use a compass anyway. So radius of 2, so it'll pass through negative 1, will pass through 3 out here. And the other part of it is the argument of z minus 1. So if I take a point z here, then that's the vector z, that's the vector 1, this is the vector z minus 1. Argument of z minus 1 had to lie between pi on 4 and negative pi on 4. So in other words, this region in here is the region it's after, less than or equal to 2, between pi on 4 and negative pi on 4. Alright, the next part asks for the fifth roots of negative 1 in mod arg form. So to do that, I'm going to start by recognising that negative 1 to the power of 5 is actually equal to negative 1. And so my first root must lie out here, just trying to centre this for a later part of the question, at negative 1. I can then draw the circle, centre 0, 0, radius 1. And all the roots we know will lie on that circle, and they'll be equally spaced around the circle. So that's negative 1. I need to divide up from there in lots of 2 pi on 5. And that would be my 5 roots starting here at negative 1. So this angle up here is 2 pi on 5, 2 pi on 5, 2 pi on 5. That means this angle in here must just be pi on 5. So this must be, I'll call this one Z1, and it'll be cosine of pi on 5. This one over here Z2 will be cosine of 3 pi on 5. This one will be Z3, which we'll say is equal to -1. This one will be Z4, which will be equal to cosine of -3 pi on 5. And finally, Z5 equals cosine of just -pi on 5. That way I've answered both questions, parts of the question including sketching the roots. In the HSC I do it with a compass and a protractor and make sure that these two roots are above each other, as are these two, to show that they are in fact the conjugate of each other. Next question asks for the square root of 3 plus 4i. So I'll let x plus iy squared equal 3 plus 4i. I can expand this part here, get x squared minus y squared is the real part, plus 2xi, 2xyi is equal to 3 plus 4i. If I equate the real part, x squared minus y squared is equal to 3. If I equate the imaginary part, 2xy is equal to 4. I'll say y then dividing by 2x is 2 over x. Sub that back over here. X squared minus 4 on x squared is equal to 3. Times everything by x squared. X to the 4 minus 3x squared minus 4 is equal to 0. That's a quadratic in x squared, so I can put my x squared in a bracket. X squared. Factorising that, -4 plus 1. This one is equal to 0. This one will not give me any real solutions, so I won't use that one. This one does. This gives me two real solutions. X is equal to plus or minus 2. Substituting back over here, that tells me that y is equal to plus or minus 1. So the square root of 3 plus 4i is equal to plus or minus 2 plus I. Second part of the question starts with a hence. That implies I must use what I've just done, or otherwise it does say to solve the equation z squared plus iz minus 1 minus I equals 0. I have a quadratic to solve over the complex field. I'll use the quadratic formula. So z is equal to -b, in this case -I, plus or minus the square root of b squared. If I square I get I squared, which is -1, minus 4 times a, which is 1 times c. c is -1 minus I. All over 2a, and 2 times a is 2. So -I plus or minus, multiplying this out gives me, and simplifying, gives me the square root of 3 plus 4i. All over 2. As I said, hence the square root of 3 plus 4i we just worked out. So we can now say the solution is -I plus or minus, from earlier, 2 plus I all over 2. Simplifying that down, -I plus I is 0, leaving with 2 over 2, or 1 as one of my solutions. The other solution is going to be -2 minus 2i all over 2, and so just in simple form, 1 and -1 minus I are my two solutions for